Hello and good morning to everyone and to my lecture of this course, EEE3130 Electromagnetism, Dr. Wan Fatin Hamama binti Wan Ahmad. We are group 6 are going to present a topic regarding to the course, which is Len'z law. Before I proceed to our content, let me introduce my member first. I will start by introducing my group leader, who is Christian Abradani bin Muhammad Daniel Philip, and he is going to present the application of the Len'z law in daily life. Next is MD Tanji Nashid, and he is going to present the history of the invention of Len'z law. The next one is me, Kusen Kai, and I'm going to present the definition of Len'z law. The next one is Nurul Hana binti Hishamuddin, and she is going to show some example regarding the Len'z law. The last member is Nur Amirul Haziq bin Noor Hisham, and he is going to present the theory of Len'z law. So I will start by my part, which is the definition of Len'z law. Len'z law states that the direction of induced current flow in circuit is such that the induced magnetic field produced by the induced current opposes change in the original magnetic field. And the direction of the induced current is determined by the right-hand grip rule, as shown in the diagram in the slide. The thumb representing the current, the induced current, and the other finger will representing the induced magnetic field. Len'z law is a consequence of the law of conservation of energy. For example, imagine if the induced magnetic field has the same direction as the original magnetic field. The magnetic field will combine and form a larger magnetic field, and this larger magnetic field will induce another magnetic field, causing it to create an endless positive feedback loop and break the conservation of energy. Len'z law is also can be stated as obeying the Newton's third law, where the Newton's third law states that every action there is always an equal and opposite direction. It's similar to the Len'z law, where the induced current will produce an induced magnetic field that is equal and opposite to the magnetic field that created it. So that's for my part. So that's all from me. I will pass the presentation to Tanjim to proceed to the history of the invention of Len'z law. Thank you.
Hello, Assalamualaikum. My name is Muhammad Tanzim Rashid and my metric number is 204928. For our group presentation today, I'll be presenting a brief history on Len'z law and the person who discovered it. Len'z law is an equation which was named after the same very person who first discovered it. In 1834, Henrik Emil Len'z first discovered the Len'z law while researching on electromagnetism. The Russian scientist was born in Depot in 1804. After completing his secondary education in 1820, Len'z studied chemistry and physics at the University of Depot. After completing his education, he went to different voyages. While on his third voyage, he studied climatic conditions and the physical properties of seawater. The result has been published as Memoirs of the St. Petersburg Academy of Science. Later on in his life, he have worked as the Dean for Mathematics and Physics Department at the University of Depot. This publishing of his was another milestone beside his other milestones such as discovering Len'z law and Joule's law. He started working with electromagnetism in 1831.
Hi, my name is Haziq bin Hisham. My metric number is 208347. I'm going to explain about theory of Len'z law. Without further ado, let's go. First, we will looking at the Len'z law formula. For the Len'z law formula, actually, Len'z law and Faraday's law use the same formula in solving any problem or question related to induced current. But Len'z law is more on the direction of the induced current, and Faraday's law is more on the magnitude. So, for the Len'z law, we will use the induced current formula, which is the turn number of coil times with the change in magnetic flux over the change for time. Next, what we need to know about Len'z law is on how does it works. The process for Len'z law is pretty simple actually. Bear in mind, Len'z law states that the induced current always flow in the direction that oppose the change in magnetic flux. So for this case, the basic thing that we need to understand is when magnet move toward the solenoid, the loop in solenoid now become north pole to oppose the magnetic field from the approaching north pole from the magnet. But when the magnet is pulled away from the solenoid, there is changing of magnetic field in the solenoid. However, the pull in solenoid now becomes south pole, which will attract the magnet back and oppose the motion of the magnet. Therefore, the induced current now become opposite direction. Lastly, I want to show you how we can determine the direction of induced current when Len'z law is applied. We can easily use right hand rule, which is we can use the thumb for the direction of magnetic field and the other forefinger used for the direction of the current. There are two scenarios, which is when magnet is come toward the solenoid and pull away from the solenoid. Since we already know about the pull of our solenoid as we applied the Len'z theory before, we can directly put our thumb in the same direction of north pole, and finally we will find out that the direction of induced current will oppose the change in magnetic flux as stated by Len'z law. So that is all about theory of Len'z law. Thank you. Bye bye.
Thank you to everyone, and hi everyone, with me Hannah, and today I'm going to present on problem solving. So in this presentation there will be two questions covered. So without waiting anymore, let's get started. So the first question will be on how to know the direction of electromagnetic field. Okay, so now as you can see from here, we have wire current and we will determine the direction of induced current. So firstly, we need to find the EMF around the wire by pointing out the thumbs into the direction of the current. So as we can see from here, the direction of the current is to the right. Hence, we need to do the thumbs to the right. Okay, to the right, and you can see from here my fingers point out while my heels point in. So and that's mean above the wire the magnetic field come out of the pitch, while below the wire the magnetic field going into the pitch. And as the current increases, where the coil increases out of the pitch, that means the coil produces magnetic field into the pitch that cancel the increasing magnetic field on that bit out of the pitch. Now to find the direction of induced current, we need to put our hand into the pitch, and we can see here the thumb of my hand are going to clockwise, hence the direction of induced current will be clockwise. Okay, so moving on to the next question on how to implement the equation into the question. So you can stop first and try to figure out on how to solve this problem. I wish you good luck, and we will see the solution on the next slide. So I really hope everyone get to find the solution on how to solve the previous problem. So let's read together, check the answer whether we get it right or not. So let's begin. So as we can see from here, the change in flux is equal to change in magnetic fields times the area cosine angle. Now we sketch a diagram to make it more clear for us. So here we have a circular circle loop and have the normal line which perpendicular to the surface, and here the radius. And the magnetic field is perpendicular to normal line. The angle theta is the angle between the normal line and the magnetic field. So, therefore, the angle is 0 degree. Thus, the cosine of 0 is equal to 1. Now, we can calculate the change in magnetic flux. So, as we know, the formula of the change in magnetic flux is the change in magnetic flux will be 4.8 Tesla minus the initial magnetic fields 1.5 Tesla. The area constant and the area is circle of pi r square, so the radius need to be changed to meter first, which will be 0.25 square meter times cosine 0, which we know already cosine 0 is 1. Thus the change in flux will be 0.648 Weber. So that's the answer for part A. So moving on to the second part, which is part B, to find the induced EMF. So to calculate, we can use this formula: negative n times the change in flux divided by the change of time, and the number of loop is 1 and it is a circular loop. So next, the change in flux, we already know the change in flux is 0.648 and the change of time is 23 divided by 1000, as we need to change from millisecond to second, and we got it as 0.023 second. So we put all the data into the equation and we got the final answer would be negative 28.17 volt. And last but not least, we can calculate the current where induced EMF divided by resistance. So we just fill in the data that we get before. So negative 28.17 volt divided by 20 ohm, and we will get the answer negative 1.41 ampere. So that's all. I really hope you understand on how to implement and solving the question by using the formula given. That's all for me. I'll pass the presentation to Christian. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Okay, my name is Christian Alpidani bin Muhammad Philip, matrix number 207300, and I'm going to explain about the application of Len'z law as well as the conclusion of our presentation today. There are several applications that are based on what Len'z law has stated. So I'll be explaining 3 of the applications based on Len'z law, which is electric and AC generator, metal detectors, and also card readers. Moving on to the first application, which is the electric and AC generator. So most electrical generators turn mechanical energy into a voltage via magnetic induction. So this shows that Len'z law states when an induced current try to maintain the original magnetic flux through a loop of wire. I'm going to show you a short video regarding to the working principle of the AC generator.
Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. 2 slip rings S1 and S2. These are connected to the armature and thus rotate with it. 2 brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown.
Okay, so now moving on. Next is the metal detectors. Okay, the operation of metal detectors are based upon the principles of electromagnetic induction. There will be a pulsing current that is applied to the coil, which then induces a magnetic field shown in the blue magnetic field. So when the magnetic field of the coil moves across metal, the field induced electric current, which also known as eddy currents, will induces their own magnetic field. This will generate an opposite current in the coil, which induces a signal indicating the presence of metal. Final application of Len'z law is the card readers. So when card readers are mainly used in the ATM cards or even in our student card also. When we see in our ATM card, at the back of it, there will be a narrow black or brown stripe at the back of the card. So actually the stripe is a very thin layer of magnetized material that has information stored in it. So this magnetic material, which is also known as ferromagnetic material, is a material that retains the properties of a magnet even after an external magnetic field is removed, where all the N and North and South poles are aligned in the same direction. So this can watch the short explanation more about the card readers.
On the back of a credit card, there's a black strip called a mag stripe. This is made up of ferromagnetic material that is laminated onto the card. Looking closer, there are tiny magnets, 20 millionths of an inch in size, which are all oriented in specific directions that carry personal information. To read this information, the credit card is swiped through a card reader. The card reader is made up of a solenoid, which is a cylindrical coil of wire, like a slinky. When a current passes through the wire of the solenoid, it creates a magnetic field. As the credit card is swiped, it causes a change in magnetic flux. Don't worry, we're going to break this down. Current is the flow of electric charge. Magnets create a magnetic field that form loops through the north and south ends. Magnetic flux is defined as B times A, or the amount of magnetic field through a closed loop with area A. Flux changes if either the magnetic field or area of the loop changes. Faraday-Lenz law explains that a change in magnetic flux, i.e. the card being swiped through the card reader, induces a change in voltage. Voltage is the change in potential energy in a circuit. In this case, a light bulb is connected to a battery which supplies 10 volts. There's a drop of 10 volts that supplies energy to the light bulb, which lights up. This represents the change in potential energy. Now using Ohm's law, I equals E over R, or current equals voltage over resistance, tells us that a current is induced through the wire of the solenoid in the card reader as the voltage increases. As each tiny magnet moves through the reader, the magnetic flux changes, changing the voltage and the direction of the induced current. A program in the card reader processes the changes in current and translates it into readable information. This then allows or denies the transaction.
Okay, so finally we have come to our conclusion. Len'z law, which is used in electromagnetism and makes possible to determine the direction of the induced current. It can be stated as a change of state of an electromagnetic system causes a phenomenon whose effects tend to oppose to this change. So without Len'z law, we may not be able to use many applications that are very crucial in our everyday lives. So I would like to thank all of my fellow team members for this interactive presentation. And I hope you guys learned something crucial in this presentation. Thank you.